The normal force is defined as a perpendicular force on an object due to contact with a surface. And it's useful to remind you of Newton's third law at this point because the normal force is always a reaction force. This means that it is always a result of the first object touching a second object, right? And then the second object exerts a force back on the first object. That second object in the normal force case is always a surface. The example that I think of is an object, a mass, sitting on the ground. If object M is sitting on the ground, we know that it has a weight force F of G. That weight force pulls down with gravity towards the surface. Because of that, that causes the object to push on the ground. So then as a result of that, the ground pushes up on the object, right? This reaction is called the normal force. The normal force is always perpendicular to the surface and is often a result of the first object making contact. What's important to note is that it doesn't always equal weight, because the weight is not the reaction force to the F of n, right? It's not the action force. The action force is applied to the ground, right? In order for Newton's third law to exist, it has to be two objects. So the two objects are the mass and the ground. So if I draw just the mass, then I'm able to analyze the free body diagram. The weight force is due to the earth pulling on the mass, and we know that the reaction force of that we talked about was the earth being pulled up by the mass. So these are the action-reaction pairs. So gravity is acting down on the mass. So then we see that the ground, due to that action, is being affected. So on the ground, there is a force pushing down, right? But then on the mass, the ground pushes up. That's your F of n pushing upward. And the key recognition there is that F of n is variable. It can change, whereas F of g is dependent upon m times g. It's just the mass times gravity. But if I had a mass and I reanalyze this, where instead of just F of g, I also took my hand and pushed down on the mass. So if I apply a force, Fa, down onto the mass, well, if the ground is strong enough such that the ground doesn't give and let the mass move down, F of g hasn't increased, right? And so the sum of the vertical forces would be F of A and F of G both acting down. And if the ground is to support that, then F of N must increase. And so in an analysis like that, then we see that F of N ends up being a larger force acting upward as a result of pushing down on the mass, right? And so we would have an F applied acting down and a larger F of N acting upward. Right? The key takeaway there is that F of n is variable and is solely dependent on touching the surface. So at some point, you can imagine that if I instead applied this force upward, right? As I apply this force upward, F of n decreases, decreases, decreases. And at some point, Fa acting up would be as large, if not greater than F of g, which means that using F of A, I'm able to lift the object into the air. And so F of n simply goes to 0, which makes sense. As soon as the object and the surface are no longer in contact, then there is no contact force, and therefore there is no normal force. Normal force becomes being able to recognize the normal force and calculate it by determining the sum of the forces based on the acceleration, in this particular example in the vertical direction only, right? Then we see that F of n minus F of A minus F of g would be equal to m times A in the vertical direction. This is how we would calculate the normal force based on the free body diagram given an applied force and an object's mass and gravity. This becomes very useful because in the next section we're going to analyze friction, and friction is a result of contact, which means that friction is dependent upon the normal force. And so analyzing the normal force is a key element of calculating friction. The most common example we'll look at, obviously, is horizontal, but we'll also be looking at an object placed on an incline. And so when I have this same mass placed on an incline like this, some angle theta, then we recognize that the weight force, F of g, is always straight down. But in this case, the normal force is perpendicular to the surface, acting outward like this. So then the friction force is a function of this normal force. And in order to determine this normal force, we'll have to do some vector resolution into perpendicular components in order to analyze what this normal force is. There is a relatively simple way of approaching that, which is actually to say that the incline can rotate the frame of reference. So rather than thinking about the mass experiencing the vertical force down and trying to resolve f of n into both left and up vectors, it's more useful to rearrange my frame of reference such that down the hill could be positive x and perpendicular to the hill can be positive y. So this is a new frame of reference for an incline situation. What that allows us to do is take f of g and resolve f of g into perpendicular components that match this frame of reference. So instead of changing f of n is already what we're now calling positive y. And so what we're going to do instead is we're going to say that this f of g can be resolved into components that are both horizontal and vertical for the incline. And so what that means is that f of g is pointing this way in the negative y direction. So we would call this f of g in the now called y direction. And then we would have f of gx, in the now called horizontal direction. We would see that these two things are perpendicular, and we would be able to resolve them based on an internal angle theta. In this analysis, then, in our summation of the forces in the y direction, we're going to utilize f of n and f of gy. And then in the summation in the x direction, we'll see that there is only f of gx. This allows us to conclude that since there is an unbalanced force in the so-called horizontal direction, which I know is not horizontal, it's now on the incline, but in the so-called x direction, there's an unbalanced force. So if there is no friction, we expect this mass to slide down the hill, right? If there is friction, of course, then there would be a horizontal force acting up the hill, f of f. And that f of f would be included in the horizontal forces. What will be key is that in order to calculate that friction force, we will be able to analyze these things in order to find the normal force. And as I mentioned, the normal force determines the friction force, and we'll talk about that in the next video.